1,261 papers in a reputed journals, and her H&X is 211. It is very high, and citations there are 2,48,900 citations. Mic off.
Mic off this.
She is doing her research interest is experimental high energy physics and collider physics, as well as dark matter sketches. And she is doing a excellent research in these fields. With this brief introduction, I would like Jyotsna Rani to continue her lecture. Jyotsna, you may continue.
Yeah, thanks a lot for inviting me for this lecture, and it's like really a pleasure to be like not in person, but online to interact with you all. I'll stop the video so that there is no network hitches. So I'll stop the video now, and like when I take the questions, I'll start again. And yeah, thanks a lot, Ramesh, for the nice introduction. So let me share the screen. And if you have any questions, so you can either ask me now or like during the talk, or you can keep the questions towards the end where you can ask me to go back to this slide, and I'll be happy to do it. So let me share the slides. Yeah. So yeah. Manage physics at the Indian Institute of Science, Bangalore, and by profession I'm an experimental high energy physicist. So I am going to talk about like what high energy physics or particle physics is. So my in the next 1 hour or so, you're going to hear about like how do we search for this fundamental building blocks of the universe using this Large Hadron Collider, which is residing. Large Hadron Collider is residing at Switzerland. So we are going to look into the details what Large Hadron Collider also. So are you all able to see the slides? Yeah, I haven't heard. Ramesh, you are able to see the slides, right?
Yes, madam. Yes, you can go ahead, madam, please.
Yes. Yeah, I'll go ahead.
Slides.
Yeah, I'll go ahead. I'll confirmation slide. Switch slides. So I'm going to talk about searching for this fundamental building blocks of the universe, specifically aiming at what we can do at the Large Hadron Collider. So this high energy physics or particle physics. Why do we do this particle physics? Just a second. Yeah. So why particle physics? So particle physics is a modern name for century-old effort to understand the laws of nature. That's told by Dr. Witten. So the aim of particle physics is particle physics or energy physics. So the aim of this field is to answer the two following questions. So what are the elementary constituents or fundamental building blocks of matter, and what are the forces that control their behavior at the most basic level? So the universe which we see around us, so what it is made up of is the first question. And if it is like made up of something like there should be some fundamental piece which we use to build the entire universe which we see around us. And in order to build not just the fundamental building block, but like we also need the forces with which these building blocks interact with, right? So we need to understand what are the forces at the most basic level. So in order to do that, what we experimentally do is we get particles to interact and study the resulting products and features. So we make the particles collide and then produce some interesting particles, and we study the final state products, and also we study the features of the produced particles. So the aim experimentally is to measure the energy, the direction, and identify these particles as precisely as possible. Of course, if the precision increases over time, and also we are going to look at that in a bit more detail. Okay. So experimentally, what we do to answer these questions is we make particles collide, either electron positron, proton proton, proton antiproton, and we look for the resulting products, and we measure whatever observables, and then try to measure them as precisely as possible. So in order to do this, we require big accelerators. Physics, we are going to look at why high energy in the next coming slides. So we need the powerful accelerators which can accelerate the particles to extremely high energies and bring them to collision with other particles. Okay. And then once we have the accelerators, we also need to make sure that detect wherever the collision happens, we can detect the particles where they collide. So we need detectors. These are gigantic instruments that record the particles as they stream out from the point of collision. So these cameras capturing the interesting events. Apart from accelerators, detectors, we also need computers to collect, store, and distribute and analyze the vast amount of data produced by these detectors. So we collect in terms of petabytes of data per year. So petabytes is 10 power 15 bytes per year. So we need not just one localized system, but we use the grid computing system, so which is like a worldwide grid. So we use computers to do it. And apart from these three, the most important thing is we need people. Basically, we need worldwide collaboration because we need to get expertise across the world containing scientists, engineers, technicians, and support staff who can not only design, build, and operate such a complex machine. So we need all these four ingredients to answer these questions. So how these ingredients are going to be used, we are going to in the next slides. So when I told the interest to study the fundamental building block, right? So if we look at our visible universe, I hope you are able to see my mouse. So that's billion meters. So the visible universe is such a big thing, okay? And if I look at the galaxy cluster, that's around 100,000 billion meters. And if in this galaxy cluster, if I look at the Milky Way, in which we are, Earth is part of it, so that is 1,000 billion meters. So if I go from the Milky Way and we look at only the solar system, that's 150 billion kilometers. So if I just look at the planet Earth, so that's 12,000, approximately 12,000 kilometers. So if I look at a footprint on Earth of almost 1 meter circle, and then go back to a sand grain is 0.5 millimeter. And then if I go deeper and look at the sand grain, what I look at is the SiO2 molecules, which are in nanometer. Nanometer is 10 power minus 9 meters. And if I go deeper, I look at the oxygen nucleus, that's in femtometer, 10 power minus 15. And if I go much more deeper, 10 power minus 18, what we get to see is the quarks. So whatever visible universe which we see around us, if we know the fundamental building blocks and how they operate, like what forces with which they interact, and of course, like not just the forces are what should I say, are dependent on the range, right? So so these building blocks, after adding up over and over again, so we can like go back in the reverse way also. Universe, we came back to quarks, but using quarks and using all these interactions at various length scales, one can go back to build the visible universe. So what everything is made up of is the basic question which you wish to answer. So if you look at structure within the atom, which is on the left side, so what you get to see is the nucleus at the center, and then around the nucleus the electron roams around. So even inside the nucleus, if you have protons, then it's made up of UUD quarks. If it's a neutron, it's made up of UUD quarks. So there are one proton and two protons and two neutrons in this nucleus. So if I look at the size if the size of the atom is 1, then in order to go back to search for this quarks, basically the fundamental building blocks, we need to go 10 power minus 18 deeper. Okay, so from 10 power minus 10 to 10 power minus 18. So far, okay, so from atom we went to the nucleus. We found the proton. Protons are not again the fundamental building blocks. So quark is a fundamental building block. So quarks, earlier it used to be called as quarks, so and the electrons are the fundamental building blocks. As of now, energy which we are able to these building blocks as of now, energy which we are able to we have discovered hundreds of particles. The fundamental ones are only a few. We are going to look at the model which explains these fundamental ones. Okay. What we do as particle physicists is, so if you look at the history of universe, so Big Bang happened, and then like there was a state of inflation, and then like over 13.8 billion years. So what we get to see is what we see as of now. Okay, so but particle physics goes back to a few seconds after the Big Bang. We are recreating the conditions just after the Big Bang. And if is there a question? Yeah, if not, I'll continue. So as I'm told, the particle physics tries to probe the early creating the conditions just after the Big Bang. So if I look at the history of the universe again, different plane. So this is like on the y-axis, temperature of the universe. On x-axis, time after the Big Bang. So we are probing almost 10 power minus 20 seconds after the Big Bang. So where we get to see these quarks. So the probes in this region. So in this temperature versus time, or if you look at the history of the universe, so we are probing this region. And in order to probe this, we need like we are going down the length scale, so we need powerful accelerators. So we are like galaxies need very big telescopes, but like in order to go deeper down and understand the matter, the deep down level, so we need powerful accelerators. So how do these particle accelerators work? So accelerate particles to high energies. Make use of de Broglie's gift to the science. So to the higher energies allow us, because energy is inversely proportional to the size. That means we need microscopes. So the higher the energy, we'll go deeper inside the matter. And thanks to Einstein, so to discover new heavier particles, we need equal to mc square, energy mass equivalence. We will hear Einstein also speak about it in the coming slides. And apart from this, to probe the conditions, to make use of Boltzmann's relation, energy is equal to kT. So we are going to the early recreating the conditions after the Big Bang. So to revisit the earlier moment of our ancestral universe and to observe the phenomena and particles normally no longer visible as of now, because like what we see the present universe is after 30 past. So but we try to go back using this powerful accelerator to revisit the older time. So but all these things we do in a controlled way in the laboratory. So to discover new heavier particles, so we use this E is equal to mc square relation. So it's available on Twitter, or now it's called as X.
It follows from the special theory of relativity that mass and energy are quite different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is quite equal to mass, amount of mass usually converges into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent. According to the formula mentioned above, this was demonstrated by Cockcroft and White in 32 experiments.
So we make use of this E equal to mc square relation to produce the particles of our interest. So what we do is we smash things together and see what is produced. So it's earlier probably it was easier to do, like throw two things opposite to each other and take a picture, but that's not the case anymore. So we have a powerful accelerator. So here the camera accelerator to collide and make them interact at different at various interaction points. So let's see. Before I move on, let me introduce the units which we use. So mass and energy in electron volts. So we measure it in volt is. So when an electron, 1 electron volt is the kinetic by an electron when it accelerates through. So when the electron passes through this 1 volt of energy gained by it is 1 electron volt. So that's it. That's 1.6 10 power minus 19 joules. These are too tiny, so we use so Einstein's mass energy equals to mass in terms of energy. A million electron volts, that's 10 power 6, or giga electron volts, that's 10 power 9, and tera electron volts, that's 10 power 12. So assuming this electron volt as a unit, we approximate the mass of the proton to be 1 GeV. So far about fundamental building blocks. Let's look at the universal forces. So I guess you're doing your bachelor's BSc, so probably you have come across these, but let me again reiterate on it. So we have strong force, electromagnetic strong force, electromagnetic force, weak force, and a gravitational force. Strong force, the force carriers are gluons, and the photon is the force carrier for the electromagnetic force, and W and Z bosons are to the weak force. And if I look at where the applicability of the strong force is, that's the main reason why we have this nucleus being built together, and also like how these hadrons, which we are going to look at, so how these are formed. And for the photons, atoms, light, chemistry, and electronics, those are the fields. And for the weak decay, I guess you might have come across this radioactive decay. So all the radioactive decay is explained by this weak interaction, and also it also explains the burning of the sun. Of course, the gravitational force, the force carrier is graviton. Haven't observed the graviton yet. But we are existing, the solar system and also the galaxies and also the black holes, everything is existing because of the, thanks to the gravitation. To talk about is like we are not on to theory of everything. So what we cover in our field experimentally as so far is a strong, electromagnetic, and weak. Gravitational also we look for some searches, but so far we haven't been successful in discovering the graviton. So, so falling and a planetary motion is explained by gravity, magnetism and electricity are unified as electromagnetic force, and weak force which is responsible for the decay. And inside the standard model of particle physics, so electromagnetism and weak force are unified as electroweak force, and we have the strong force which is responsible for these nuclear forces. So the standard model explains only the unification of electromagnetism with the weak force. So what we have is the electroweak force, and then the strong force is not a standard model. And then there is grand unification where electroweak force and the strong force are also unified, and the string theory which aims to do the unification of gravity also, that is called the theory of origin. So I just mentioned about the forces as forces. So let's look at how these forces are used in our accelerator. So all the forces can be thought of as interactions between these elementary particles. It's almost like a person is throwing a ball, and the other person, a person is throwing a ball over here, and the other person is catching that ball over here. So thanks to Feynman, so we use these Feynman diagrams. So that's Feynman, Richard Feynman. So we use these Feynman diagrams to explain the electron interacting with an electron through an exchange of force. Okay, so all the forces are mediated by this force carrying particle. That's the quanta of the field, or that's called the photon for the electromagnetic force. So this diagram represents a Feynman diagram, and this is for two electrons each other. Mentioning about the standard model of particle physics. So this is almost like if you have learned chemistry, so you have this table of elements, right? So here for us, the standard model of particle physics is almost like the elementary table in the chemistry. So what we have so far, we have discovered is we have looked at these matter particles which are leptons, and then the quarks which are making the hadrons. Basically, we are going to look at what hadron is. So in the lepton sector, electron and the electron neutrino, and in the quarks generation, the quark sector, up and down quarks. So the first generation is the stable generation. So the second and third, those this is the second generation and this is the third generation. These are not like some of them are available by default, like the muon is we can get it from the cosmic rays, but some of them we produce them in the laboratory, and then they decay to these first generation. The second and the third generation, or like not the stable ones, so they decay to the first generation of the leptons and quarks. So there are three generations of leptons, three generations of leptons, and three generations of quarks. And apart from that, when we are looking at the force particles, the electrons interact through the photon electromagnetic force, and they also decay through the W and Z electroweak force. And then when it comes to the quark, so they interact through the strong force, and the gluon is the main force carrier for that. And apart from that, we also have Higgs, which is of 125 GeV, which gives the masses to all these particles. So the origin of mass for these all these fundamental building blocks is explained by Higgs boson. It took quite some time to discover it, but like yeah. So in 2013, the Nobel Prize is given to them. Okay, yeah. So we are going to look at the details. So let's look at in my title of the talk, I wrote Large Hadron Collider. So large because it's a 27-kilometer circumference ring. So this is 27 kilometer big, and the Large Hadron Collider, simply known as LHC, is the world's largest and most powerful particle accelerator. And we have two general purpose detectors. Apart from that, there are two more detectors, the four general purpose, but CMS and Atlas. So I have worked on Atlas earlier, but like at the moment, India is part of CMS experiment, compact muon solenoid experiment. So IISc, after I joined IISc is part of this
Can you get
CMS experiment. So this, yeah, so this LHC, probably I'll take the questions towards the end. If you have any questions, keep them towards the end. We can go back to the slides and then we can discuss. Because it's online, if I cut the flow, then it will be hard to go back to the flow. Okay, so please keep the questions towards the end. I'll come back to it. I'll be happy to answer the questions I'll be happy to stay for some more time. No problem. Okay. So LHC, this Large Hadron Collider, acts as a super microscope operated at center of mass energy of 7 TeV. We started data taking in 2010 and 2011, and also at 2012 we have this 8 TeV after we collected enough data from 7 TeV and 8 TeV. So in July 2012, the Higgs boson discovery was announced. And then after that, we started collecting data at 13 TeV center of mass energy. TeV stands for tera electron volts. That's 10 power 12 electron volts. So from 2015 to 2018, and then there was a long shutdown to increase the accelerated energy. So now we are colliding at 13.6 TeV, and that started from last year, 2022. And here we collide protons with protons. Okay, so not protons and antiprotons, but like protons and antiprotons. Protons and protons, they are circulated in counterclock, like opposite directions, and they are made to collide at this detector, CMS detector, and also the Atlas detector, and also there are two more, LHCb and Alice detector, but like those purposes are slightly different. So CMS and Atlas are being the general purpose detectors. So we use these detectors. So let me just introduce you what Large Hadron Collider is. Hope you are able to hear. I'm increasing the volume so that you can hear the video.
Protons are automatically sent to forming stacks together to create silicon particles.
So this is almost like, yeah, we just finished Deepavali festival, so it's almost like, of course, like we don't get to see this kind of splashes outside, but this is only a representation saying that inside this detector, these kind of splashes happens, and then we use this splashes of particles to use the reverse engineering to go back and build the interesting particles which you are searching for. So just a side note, so like this is 13.8 billion years ago, probably there were like aliens who built this large particle collider, and that's why they have accelerated and they made the present universe. Okay, so the main interest is study the physics laws of first movements after the Big Bang. So large because it's a 27 kilometer circumference ring. That's the biggest so far. Of course, like we plan to have 80 kilometer, but like that's like long future. Okay, so 27 kilometer circumference. That's why it's a large collider. And hadron because hadron collider. So what is a hadron? So in particle physics, a hadron is a composite particle made up of quarks held together with a strong force. So hadrons are categorized into two families. So if 3 quarks are put together, those are called baryons, and if a quark and antiquark are put together, those are called mesons. So, okay, so proton and neutron are baryons, but like simply we are using protons and protons to collide, but like we use the word hadrons. So this, so we are colliding proton over proton. That's why it's a hadron collider. So Large Hadron Collider at CERN, Switzerland. So here I'm also mentioning that it's a broadband quark and gluon collider. So even though we are colliding this proton and this proton to like at the moment to 6.8 TeV each, so the center of mass being 13.6 TeV, we don't convert this entire energy into the interesting equal to mc square and then interesting particles. So what happens is one of the quark from this proton or a gluon from this proton interacts with one of the quark or the gluon from this proton. So that means even though the proton has an energy of 6.8 TeV as of now, but the part of it, either the quark or the gluon, they'll only carry part of the energy. So that's why the center of mass energy for this partonic interaction is not exactly the center of mass energy of these protons. So it could start from 1 TeV up to certain TeV. So that's why it's called as a broadband quark and gluon collider, because these are composite particles. The protons are composite particles. That's why we have to deal with broadband quark and gluon collider. So why we are interested in this hadron collider? So they have a history of discovery. So the W and Z bosons, which are the force carriers for the electroweak force, the weak force, they were discovered in 1980s at CERN. And the top quarks in 90s was discovered at Fermilab. Of course, like at Fermilab, it's a proton antiproton collider, and also for the WZ bosons, it was proton antiproton collider. And on 4th July 2012, so the discovery was made by, it was called as God particle was discovered at LHC. So that's the Higgs-like boson discovery at Large Hadron Collider, where we are colliding proton over proton at CERN. And then it took almost like less than a year to say that it's actually a Higgs boson, because like we are not just saying that it's an observation, but like we need to study the properties of the particle. So after we have enough time to study the properties of the particle, we said on 14th March 2013 that it's a Higgs boson at Large Hadron Collider. So long shutdown began in 2018, and then we took data from 13 TeV in 2015 and 2018, and after this long shutdown, we started data taking again last year. Due to COVID, it was delayed for more than a year. So at the moment, we are running with 13.6 TeV. So that's about the introduction. So okay, so we are colliding protons over protons at the center of mass energy, let's say 13.6 at the moment. So how do we go from this collision data and say that we have found this Higgs particle, or we have found this top quark? So how do we go doing that? So we work on this compact movement solenoid. So that's why I'm biased to showing the details from CMS. So we are so at CMS, protons come in one direction, and the other set of protons at the same center or same energy come in the other direction, and they collide at the center of the detector. And what happens at the center is like this splash of particles are being produced thanks to E equal to mc square. So we basically produce variety of particles. So here, what is happening here is described by, because protons, we use the quantum chromodynamics to describe the strong force, and that's being shown by the theory over here. And experimentally, what we get to see is like when we plot the distribution, so we see a kind of peak structure over here. So this is the theory, and this is what we experimentally see, and then we confront the theory with what we have seen, and then we try to either discover the particle or rule out the theory. So how do we go about doing this? That's what we are going to look at in the next set of slides. So before we move on, let's quickly look at the compact muon solenoid detector. I'll be slightly faster. It's 346. So this is a gigantic detector. So it's like 14,000 ton 3D camera with capacity of taking 75 megapixels at 40 million photos per second. So if I look deeper inside the detector, so what we have is like here is the collision happening. So that's we call as a beam pipe, and it's surrounded by various set of detectors. Let me just give you an idea. So it's almost 12,000 tons of material, and overall diameter, the diameter is 15 meter and the length is around 20 meters. So we operate the magnetic field at 4 Tesla. So we have different layers of detectors. So due to lack of time, I'll not go very much in detail. So we have the beam pipe where the collision happens, and then that is surrounded by the tracker, which is made up of silicon, and then we have the calorimeters to absorb the energy. So electromagnetic and hadron calorimeter, those are embedded in the solenoid field, and then we have the muon detector at the end of the detector. So how do we detect the particles coming out of this collision? So if we are looking at the heavier particles like Higgs, W, Z or tau, they are heavier, so they decay into lighter ones like electron, muon, photons or pion, and which travel to the detector and create the electronic pulse. So if I am looking at, like, this is the coordinate system, x and y, and then the z is in this direction, and if I look at only the cross section of the detector and look at this sector, so what is happening from here to here, almost 10 meter. So if a particle is produced, then it interacts with various layers of this detector, and typically 5 types of particles are produced, and that's what we detect, and then we use the reverse engineering to reconstruct the particles of our interest. So let me just briefly show you. If I am looking at the muon, muon basically passes through the tracker. It doesn't leaves little bit of energy in the calorimeter, but it leaves a trace in the muon detector. And here the 4 Tesla is a magnetic field and the 2 Tesla is a magnetic field because of the direction is different, so the curvature of the track is different. And if I'm looking at the electron will leave a trace here, and also it will leave the energy in the calorimeter, electromagnetic calorimeter. And if I'm looking at the charge hadron like pion, then it will leave a trace in the tracker and then leave entire energy in the hadron calorimeter. And if it's a neutral hadron, it will not leave any trace in the tracker since it's not charged, so it will leave the entire energy in the calorimeter. Similar to the photon will leave, it interacts electromagnetically, so it will leave the energy in the electromagnetic calorimeter. So we use these features of the final state particle, and we use the reverse engineering. We collect all the information from the various sub-detectors and then do the reconstruction of these objects, electron, muon, photon, charged particles are basically hadrons. So as the stable particles are produced, they traverse various detector components and they leave their characteristics in nature. So this is like the tracker, calorimeter, and the solenoid, and then the muon detector. So if we are looking at, like, let's say the neutrinos or the dark matter, so what happens is, like, there is a imbalance in energy in the transverse direction. So whatever is missing out, that's what we say as the attribute to the neutrino or the dark matter. So just to give you a glimpse, so what happens at the proton-proton collision is, like, this is what, like, some kind of Diwali thing, but of course, like that, this happens, everything happens inside the detector. So we are creating approximately 1 billion mini Big Bangs at LHC every second. So, okay, we are colliding protons with protons at these high energies. So what do we expect to see? So if I look at the x-axis, it's the the particle mass, and if I'm looking at the y-axis, it's basically the probability of occurrence of this event in cross section, or in terms of event rate in hertz, okay, gigahertz or so. So the collision rate happens at gigahertz, but what I am interested in is, like, in the physics, which has, like, very low possibility. The cross section is very low, and also the event rates are very low. So what happens at here is, of course, like we are proton, single proton do not collide. So what we do is we make them into bunches. So these bunches are made to collide at 40 megahertz. And then what happens is, inside this bunch only the protons collide, some of the protons collide at this gigahertz rate. And then even in these protons we are interested in either the quark or gluon, which are part of it, so the parton collisions. And then that should produce a new particle, so either the Higgs or supersymmetry or something else. So that's from 40 megahertz to let's say 10 power minus 5 hertz. So like we are going over here. So event rates are typically 1 billion per second, but we have to select interesting events 1 in 10 power 13. So the same picture is shown over here. So let me just give you a hint, idea of the collision point. So the quark, protons and protons are collided, but like those are not fundamental. So what happens is, one of them, quarks of different proton, begin to feel each other with the gluon exchange as they come closer, and then using this quantum chromodynamics, they are stretched and the gluon snaps into either top antiquark, or they produce Higgs boson. So top quarks are quite heavy and hence couple strongly to Higgs bosons. Here they could radiate a real Higgs boson. So once the Higgs boson is produced, Higgs or top, any particle which is unstable, it's not, it decays to the stable particle, it decays to 2 Z bosons, and these Z bosons decay to muons. So we have at the end 4 muons in the final state. So using these 4 muons, we have to do the reverse engineering and reconstruct the mass of the Z boson, and then go back and reconstruct the Higgs boson. So as I told, 40 megahertz to few hertz which we need to collect. So the collision happens at 40 megahertz. So we use, okay, probably this is not that interesting. Let me explain it in a simple term here. So we use something called as a trigger, or the online event selection in real time. So 40 megahertz is the collision thing happening at the detector. So we have something called as a buffering system. So front-end pipeline and readout buffers. So at Atlas detector, they have put it as level 1 and level 2, and at CMS we use as level 1. And from 40 megahertz we reduce it to 100 kilohertz, and then we have this computing firm, so event filter. So that after it passes to this processing firm, so what we get to collect on tape or on the disk is of the order of 100 hertz or so. Similar thing. Okay, the detector system is like the trigger system is slightly different. So let me explain the trigger in a simpler form. So level 1 is a custom hardware and firmware. It reduces the rate from 40 megahertz to 100 kilohertz. Here the advantage is speed, and also for the level 2, it's a computing firm, the software. It reduces to few kilohertz, and it basically reconstructs only interesting region around the interesting object. And at level 3, it's completely software. We have a computing firm, and here the only after the selection at the level 3 stage we keep the interesting events. So here advantage is the best reconstruction. So we at CMS we have level 1, which is a hardware and firmware based. Basically we are devising algorithms on chips. So the FPGAs, if you have heard of them, so that's being used at level 1, and level 2 and level 3 we are put together and we call it as high level trigger. So let me explain this in very simple terms. So real time event selection. So let's say I am looking for the Higgs selection using the trigger. At level 1, what information we have in this 4 picture is like it's not clear. So not all the information is available, and it has coarse granularity. So, but if we go to level 2, so we have slightly improved reconstruction. So I'm looking for Higgs. So what I do is like, okay, I found something. I'll only look at the interesting region, so region of interest, and then do the reconstruction. So using this, I can say that okay, these still look like Higgs, but not the this part. So I discard this and I only keep these 3 events for the further selection. And at level 3, we have all the fantastic computing firm and good reconstruction. So what happens is, okay, this is not Higgs, so we discard this event also. We have level 3 high quality reconstruction algorithm using the information from all the detector. Of course, we cannot do the entire selection while we are collecting the data. So we do have the background. So we do collect Feynman also apart from Higgs. Okay. So this is Peter Higgs and this is Richard Feynman. So we collect this interesting event in real time and then store them in the hard disk or on tape, and then we do offline. We'll have a lot of time to dig into this and then discard the background and keep only the signal. So as I mentioned, the LHC computing grid, we are using this grid computing system. And if you're not aware, so the World Wide Web, which everyone is using, and it's part of our day-to-day activity. It's invented at CERN. So the 30th anniversary of WW was happened in 2019. So the grid infrastructure provides, that means like we are connected with the data at CERN, but like we have a computing firm, let's say, we have it for CMS, we have a system at TFR Mumbai, because like that's the T0, the TFR started the collaboration with CMS from quite beginning, and the new institutes have joined very recently. Okay, so the data is connected in various countries from CERN, and then we do different activities, and then we pass on the information back to CERN, and the data is available for everyone to use who are part of this network. So that's what we call as a computing grid or the grid computing system, which is again due to the needs of our experiment, we have established that. So let's look at this trigger a little bit again. Data is collected online, collision data recorded by the detector, and a physicist analyzes this data offline. Offline means we have a lot of time, not like there is no data taking, it's already there available on the disk and it's been reconstructed, and then we have enough time to optimize and model, do the discovery of the new physics. So online we have looked at, so let's look at the offline data analysis. So data analysis change, so we collect the data from many channels, many sub-detectors, millions and millions of them, and at the real-time event selection, that's called as a trigger, we read out everything or throw the event away depending on whether it satisfies the need, and build the event. We'll put the information together from all the detectors, sub-detectors, and then we store the data. Once we would like to analyze it, we'll store the data. And later, offline, we analyze them, we do the reconstruction, then the user who develops this analysis algorithms and also reduces the volume of the data. And this is only for data, but like we have to confront the data with the theory. So we simulate the theory samples, not just the signal samples, but also the background samples, and we reconstruct and we apply the analysis algorithms, and we also do the data volume reduction, and then we compare the real data with the theory. Basically, with the theory means with the simulation. So from here on the top left to the bottom right, we do the comparison. So let's look at the data acquisition chain. So this is called as DAC chain. So detector front end means what are the electronics which are sitting on top of the detector. So the trigger system looks like this. This is only like a miniature representation. It will be slightly huge. And then we have a readout system. And once the trigger says, the online event selection says yes or no, depending on yes, it will get stored. It will go to the high level trigger selection, and then it gets analyzed with this computing firm and then gets stored in tapes. Okay, not in these floppies, but we have robotized system to access the data also. So from megahertz, so what happens is we reduce the rate to 100 hertz at the high level trigger or online reconstruction stage, and then we store the data. So once we store the data, so then we do offline reconstruction. Basically, we have already seen how the muon interacts, how the electron interacts, how the hadrons interact. So using the subdetector information, we do the offline reconstruction. Apart from that, we also need to calibrate these objects, and we also do this alignment of the detector. And then we store, this is the further data storage, and then the reconstructed data is stored, and then the user analyzes this data, and the user comes back with these histograms of different and also confronts it with the theory. Okay, so you see the data points, and also there is a data points are from the data, and then the theory points you get to see different modes. Okay. So here also, if the data volume reduction, which I am talking about, we start with petabytes of data, and once the reconstruction happens, it becomes to terabytes. And what we analyze at the end, it's in terms of kilobytes of data set. Okay, so I'll just quickly go through this. So when a particle passes through a detector element, so then we have to do this digitization and reconstruction. So what we get is analog signals, and then from the analog signals we have to develop this algorithm and say, okay, if these are the hits in the detector. So then there are different hits, like let's say this is this point, and this hit is this point. And from these hits, which have this 3 x, y, z and time position, using this we have to do this track finding and track fitting. This is for the charged particle, and this is the helix. So then it's inside the magnetic field. So we reconstruct the momentum of this track. And we store this information for each and every event and each and every track after the selection. And for each event, there are like different number of charged tracks, and the data is stored like in event 1, number of charged tracks are 2, and then we store the momentum of each track and the charge of each track. So similarly for the event 2. So simulation workflow, okay, for the data, we are colliding in real time, and then we are producing the data, electronic signal, and we are doing the reconstruction, digitization and everything, and we are converting them to the observables, which are easy for us to analyze. But for the simulation, which is based on the theory, if you want to use a model and then confront the theory with the model, so we simulate the physics interaction. We use we have different Monte Carlo simulators for doing it. Pithia, Herwig, name it. So what happens is I'm interested in producing this electron positron, so I produce this in the simulation, and also I produce the background samples which mimic this electron positrons in the final state, and then I put this physics simulation through the detector simulation. So how these electrons propagate through the detector, including the bending of this charge track in the magnetic field, leaving hits in the detector elements, and also how interaction with the material of the detector, calorimeter, and everything is done through this detector simulation. So we have to, for the simulated samples, physics simulation, then detector simulation, and then electronic simulation, and then we do the digitization and everything, and then we do the reconstruction, which is same as what we get to see from the real data. So the simulation step is very CPU intensive, and then it requires a lot of computing resources. That's why we have this grid computing system which is of our help. So even in simulation, we process the detector simulation, we store the data, and we do the reconstruction, offline reconstruction. So we follow the exactly same steps as the data for the offline analysis chain. So in simulation, we produce billions of events, because these cross sections, or the probability of occurrence of these processes is pretty low. So we simulate this proton-proton going to Z boson or proton-proton going to Higgs, and we also add the detector response to the produced particles, and we understand the detector response and analysis parameter, and only after that we compare the simulation with the real data. Okay, so just a note here is simulations are not just used once we have the data, but like in order to even build the detectors or sorry, I was using this full screen, so I could not see whether when I got disconnected. So let me just share.
Jasna, we could not hear you. Okay. Now we can see your presentation.
Can you hear me now?
Yes.
Okay.
We can. Okay. Thank you.
Yeah, I have unmuted myself, so you should be able to hear. And let me go back to the. Yeah, so the network glitches happen. Yeah. Okay, so let me just quickly say simulation we do. So our task is to look at this reality and confront with the theoretical model. So we experimentalists we intend to fill the gap. So we see in reality we see a splash in the detector, and then flash of particles in the detector, and then we confront the theoretical model. So if I look at the theory model, if you're not yet familiar with Lagrangian, it's fine. But the standard model is contained in this Lagrangian, so it contains various parameters. So it has coupling constant, masses, and this standard model predicts like there are physical observables which we can measure experimentally. So those are called as the cross sections, branching ratios, or lifetimes. So that's what the theory gives us. But experimentally, how challenging it is. So see, like if I only have a register, an address of the register, and then the value, what the electronics wrote out. Okay, so this is 1/13th of an event in the detector. So we get about 100 events per second, for an example. So we have to convert this electronic signal using different algorithms, optimized for the signal also, calibrate it, and then say that this is an electron, or this is a photon, or this is a muon. We have to do this complex thing, and then we have to confront the theory. So the experimental aspects are a little bit like it, of course, like it has engineering elements, but it has also the physicist input. Okay, so this is such a complex thing we tackle experimentally, and then we confront the theory. Okay, So we use this imperfect measurement of interactions in the detector. That's what we call as raw data. And then we reconstruct the events. So that's a unique happening. Let's say in a run, event number 1345, it contains a event which has this Z boson decaying to 2 muons. And the observable, which the theory gives, is cross section or the branching ratio or some lifetime. So once we analyze, what we do is we confront the theory with the experiments by comparing the measured quantity. So like we basically look at this cross section majority of the time and then confront the theory with the measured experiment, what we measured. So the analysis flow looks like this. So whatever is on the left side is for the real data. So that's the detector and trigger. And then we use the reconstruction algorithms, and then the user uses different things, physics analysis. And on the right side, simulated data, it's not only the signal model, but also the backgrounds which mimic the signal. So that we simulate the data and we do the reconstruction same as what we do for the data, and then we do the physics analysis. So the two steps are centrally produced by collaboration, and the physics analysis is individually done or done by a small analysis team. So then later we compare the theory with the experiment. So theory is on the right side, the simulated data, and the experimental observation is coming from the left side. So that's how the analysis workflow happens. And let me spend a few minutes in explaining what we have achieved so far, the standard model and the discovery of Higgs. So the production of Higgs, this is again a simple thing, simple typical explanation. So the Higgs boson is responsible for explaining the origin of mass. So the particles interact with the invisible field and acquire the mass, and the theory predicts that this field particle, the associated particle with this field is called as a Higgs boson. So the Higgs bosons would decay instantly to lighter particle. It could be 2 photons or 4 muons. So we have to be like detectives to look at these final state particles and then do the reverse engineering and then look for the evidence to see what happened. So identifying the collision of interest. So as I told that Higgs goes to Z. So first we have to reconstruct Z to mu mu. So Z to mu 2 muons will be reconstructed. So if this happens in billions of collision events, so we look for these patterns produced by decay products of heavier particles. So we analyze petabytes of data, then we convert into terabytes. Okay. And then both LHC experiments presented their results on 4th July. Left side is Fabiola. She was Atlas spokesperson, but like now she's the CERN directorate. And right side is a CMX spokesperson, Joe in Kerala. So they both told that, okay, we have seen the Higgs boson. We found the Higgs boson on 4th July 2012, and it was like that made a lot of physicists very happy, and it's a big giant leap for science because we took almost 60 years to discover it. And for the first time, Francis Englert and Peter Higgs, they met, who got this Nobel Prize. So the Higgs mechanism was given by all these physicists, but Kibble, Gurang, Hazen, and Braut, they are no more. That's why the Nobel Prize has gone to Englert and Higgs. So nearly 50 years ago, 6 physicists proposed an explanation of how particles get mass, that's the Higgs mechanism. And in 2012 we discovered it, and 2013 these people got the Nobel Prize. Okay, so how does it look like? So we look for this bump, basically like some kind of resonance or so at 125 we see that there is like a huge excess. And this is for the 4 leptons, basically 4 muons. And if the Higgs decays to 2 photons, we see a bump like this. Like this is the freely falling background distribution, and then we see something peaky over here. That's the Higgs boson. So at 125 GeV, we have discovered this Higgs boson. And 10 years ago, they both observed this Higgs when we have very little data. But after 10 years later, what we get to see is using full run-through data, we can clearly see the peak of the Higgs boson at, okay, this is for Atlas and this is for CMS detector. We had a lot of events. And also we have first indications of rare Higgs boson decay. Probably I'll skip this. So, and also we measured this Higgs boson self-coupling recently. So if I look at this success of standard model, okay. So if I look at on the x-axis, it's various production mechanisms. Sorry. Various production mechanism, W boson, Z boson, up to 2 Higgs boson, double Higgs bosons. And if I look at on the y-axis, it starts from 10 power minus 4 picobarns up to 10 power 5, almost 10 power 10 orders of magnitude. So we are scanning at various center of mass energy, 7 TeV, 8 TeV, and 30 TeV, and theory prediction. So we are able to reconstruct and also confront the standard model, and we are celebrating the success of standard model. Standard model has given precisely the cross sections for all these processes. Of course, like in some cases, if we haven't
Just now we cannot hear you.
yeah, can you hear me now?
Yes, yes. Now
Yeah. So yeah, I got disconnected while I was on this slide. So I'll a few minutes. I'm almost close to my talk. So the standard model has successfully measured or been represented by experiment, and with 10 power 10 magnitude we are able to see. So when we go beyond the standard model, one theory we have the supersymmetry. So whatever standard model we have, so we also have super partners. So why we went to supersymmetry is it predicts a viable dark matter candidate. Of course, if it exists. So far, we haven't got any hint for the supersymmetric particle. So the dark matter explains this outstanding mysteries of the universe. So when we look at the rotational curves of this galaxy, so what we expect to see is this curve, but the measured data basically showed this. So
Josna.
this basically gave us a hint. Yeah,
Excuse me, Josna.
yeah,
We cannot
yeah.
see your presentation. We cannot see it.
I'll share it. I'll share again. Okay, sorry. Somehow, yeah. Now we should be able to see. Yeah, so that's the success of the standard model. And when we go beyond the standard model, what makes us to go beyond standard model is like there are certain things which are not explained by the standard model. The Higgs boson mass as well as the dark matter candidate. So supersymmetry is one of the models to explain the dark matter candidate. So for these, the left side you have the standard model particles. So what the supersymmetry says is we have super partners for all these standard model particles. So those are the super partners on the right side. So, but we haven't yet discovered the super partners, any of them to see. But the dark matter is really like we got it from the astronomical observation. So when we look at the rotation curve of this M33, so what we expect to see theoretically is this green curve, but experimentally what we have observed is what we get to see is this. And also when the bullet cluster collided using the gravitational lensing, what we get to see is the blue matter exists, and that's the dark matter that's inferred by the gravitational lensing. So there is a matter which is like interacting only through gravitation, but it's not visible. That's why it's dark. It doesn't interact with any other interaction. So that's why it's called as a dark matter. So probably what is dark matter composed of is one of the questions. So supersymmetry particle perhaps, or even the light as supersymmetric particle probably has the right properties of this dark matter. So dark matter has an empirical evidence from the astronomical observation. It interacts gravitationally only. So it's electrically and color neutral, and it's long lived. So we are making use of not the gravitational interaction, but we are making use of the electromagnetic interaction, strong interaction, weak interaction, interacts gravitationally only. So we have to use this invisible particle. Basically, as a neutrino, it doesn't leave any trace, and the dark matter doesn't leave any trace inside the detector. So there are three different mechanisms of how the dark matter is produced. But what we are interested is at the particle collider, the standard model particle. Basically, proton-proton collides, and something happens in between, and it either produces the dark matter particle or the standard model particle. Using this final state particle, we infer and go back to whether we have produced the dark matter or not. So if we look at the recent results, so supersymmetry or the dark matter search. So we expect to see like the blue, this is the data points, and the blue is the theory on the left side plot, but we haven't, the data agrees very well with the backgrounds. So we haven't seen any excess over the background. And similarly on the right side, it's again one more production mode. So it very well explains the data is very well explained by the backgrounds only, and if we expected to see the signal, it would have been here. So we haven't searched for any supersymmetric particle or the dark matter candidate. So the quest continues. So why we are interested in all this is like universe composition. If we are looking at it, so we have heavy element, neutrinos, stars, free hydrogen and helium, everything put together, approximately 5%, and the rest of the dark energy in dark matter, it's a mystery, about 95%. So a lot of new challenges, but many exciting times ahead. So conclusions from this is we able to tackle some of the questions in physics. So at least Newton's unfinished business, what is mass, what is the origin of mass, was explained by the Higgs boson discovery at LHC, and still there are open questions. Higgs did not answer everything, so there are still open questions. What is 95% of the universe made up of? We do not have any hint of it. And why nature prefers only matter? Why there is no antimatter? We don't see any antimatter here. And the secrets of the Big Bang. What was matter like within the first second of the universe alive? And is physics unified? Can we unify the gravity along with all the other three forces? So all these questions are still open. So we are still looking for the answers for this. We haven't discovered supersymmetric particle also. We are still looking for answers for this. So since I'm part of this India CMS collaboration, so all these universities which you can get to see, University of Hyderabad, which joined from Andhra Pradesh or Telangana from like a few years ago, India CMS, and we are funded by the DST and DAE. And the CMS collaboration consists of almost 40 countries, 200 institutes, and more than 4,000 members. And I visited a CMS experiment back in 2019. Now I cannot go and take a picture like this because it's closed and we have data collection going on. So if you are interested, you can contact me on my email ID is this and the web page is this. And also you can look at some inspirational video. Thanks. Any questions? If you have any questions, feel free to ask me now.
Thank you, Josna.
Yeah, if you have any questions, I'll be happy to answer. Sorry, I took quite long.
Thank you very much, Josna. And here are some students who want some questions, ask some questions.
Yeah.
But they'll ask questions in Telugu only.
తెలుగులో హాయిగా అడగండి, ఏమి తొందర లేదు, నాకు తెలుగు బాగా వచ్చు. నేను చదివినంత తెలుగు మీడియంలోనే, ఏమి చింతపడకుండా అడగండి.
Good evening, ma'am. Good evening, ma'am. I am Tej from BSc final year, MPCS.
Yeah.
I had a doubt. Why they are using synchronous cyclotron in LHC?
Oh, why we have used that's like long back.
Why they are using synchronous cyclotron in LHC?
No, but like we are using that long. Yeah, that we have used long back. Now we don't use that. That's only for the WC goes on observation.
Thank you, ma'am.
Yeah. Any other question?
Good evening, madam.
Yeah, good evening.
My name is Akila. I'm second MPC. మేడం, మనం జనరల్ గా ఫస్ట్ ఏవైనా కూడా మాలిక్యూల్స్ గా నిర్మించబడి ఉంటాయని అనుకుంటాం కదా. ఇప్పుడు మాలిక్యూల్స్ కూడా ఆటమ్స్ గా నిర్మించబడి ఆటమ్స్ కూడా ఎలక్ట్రాన్స్, ప్రోటాన్స్, న్యూట్రాన్స్ అన్ని ఉంటాయి అనుకున్నాం కదా. ఇప్పుడు మళ్ళీ హిగ్స్ అని చెప్తున్నారు. హిగ్స్ కన్నా చిన్నవైన ఏమైనా ఉంటాయా మేడం?
సో అంటే మన మాలిక్యూల్స్ ఆటమ్స్ తో నిర్మించబడ్డాయి, బట్ ఆటంలు కూడా ఎలా నిర్మించబడ్డాయి అని మనము తెలుసుకున్నాము. న్యూక్లియస్ ఉంది సెంటర్ లో, తర్వాత ఎలక్ట్రాన్స్ చుట్టూ తిరుగుతున్నాయి కదా. న్యూక్లియస్ సెంటర్ లో ఉన్నది కూడా అది కూడా డివిజిబుల్, అది కూడా విభజించబడుతుంది. కాబట్టి విభజించి చూస్తే మనము దాంట్లో ప్రోటాన్ న్యూట్రాన్ ఉంది, ప్రోటాన్ న్యూట్రాన్ లో క్వార్క్ ఉందని తెలుసుకున్నాము. హిగ్స్ వరకు వస్తే మనకి ఏమి అంటే ఈ ఫండమెంటల్ బిల్డింగ్ బ్లాక్స్ ప్రోటాన్ న్యూట్రాన్ క్వార్క్ అని ఎలా మాస్, తెలుగులో ఏమంటారు, నాట్ ద తెలుగు మాస్, నాగార్జున మాస్ సినిమా కాదు, బట్ లైక్ వీటికి బరువు ఎలా వస్తుంది అనేది హిగ్స్ బోసాన్ చెప్తుంది. సో మనము ఆటమ్ లోపలికి వెళ్తే తెలిసింది ఏమి అంటే క్వార్క్స్ న్యూక్లియస్ ని బిల్డ్ చేస్తాయి, ఎలక్ట్రాన్ న్యూక్లియస్ చుట్టూ తిరుగుతుంది అని తెలుస్తుంది. అండ్ వీటికి మాస్ వచ్చింది, వీటికి బరువు ఎలా వస్తుంది అంటే హిగ్స్ తో ఇంటరాక్ట్ అయిన తర్వాత బరువు వస్తుంది వాటికి. ఓకే, థ్యాంక్ యూ. ఇంకా ఏమైనా క్వశ్చన్స్ ఉన్నాయా? ఓకే, ఉన్నాయా? సరే, నేను సరే ఇంకొకసారి అడుగుతున్నా. సో హిగ్స్ బోసాన్ మాస్ కనుక్కోవాలి అంటే మేము మళ్ళీ డీటెయిల్డ్ అనాలిసిస్ చేస్తాం అనమాట. సరే, హిగ్స్ ఇప్పుడు టూ ఫోటాన్స్ లో డికే అయింది కదా, ఫోటాన్ తీసుకుని వచ్చి దాంతో ఇన్హెరెంట్ మాస్ అని ఒకటి ఉంది, మాస్ ఇచ్చేస్తాం. సో అందుకే అక్కడ 125 GeV దగ్గరే వస్తుంది. ఓకే, మనం ప్రాపర్లీ క్యాలిక్యులేట్ చేసిన ఫోటాన్స్ తీసుకొచ్చి మేము మెజర్ చేస్తాం కాబట్టి 125 GeV అని తెలుస్తుంది. అది కాకుండా ఎల్హెచ్సిలోను ఇంకా ఫర్మి ల్యాబ్ అక్కడ షికాగోలో ఉంది కదా, అక్కడ కూడా సెర్చ్ చేసినప్పుడు మనకి మాస్ తెలియదు కాబట్టి అప్పుడు మాస్ ని వేరీ చేస్తూ నిండా అనాలిసిస్ చేసాము. అప్పుడు చేసిన తర్వాత ఏమైంది అంటే లైక్ ఇక్కడ మేము వెతికాం కానీ మాకు దొరకలేదు అని ఎక్స్క్లూజన్ రీజన్స్ ఉండేవి. అందుకు మాకు ఈ రీజన్ లోనే దొరకవచ్చు అన్న హింట్ చిక్కింది కాబట్టి చూసి మెజర్ చేసామన్నమాట. ఓకే, ఇంకా ఏమైనా క్వశ్చన్స్ ఉన్నాయా?
Good evening, madam. I am Hema from 3rd BSc MPCS. Madam, Higgs boson అనేది గ్రావిటేషనల్ ఫోర్స్ కి వెర్చువల్ పార్టికల్ అవుతుందా మేడం?
లేదు, హిగ్స్ బోసాన్ అనేది గ్రావిటీతో ఏమీ ఇది లేదు. అది కంప్లీట్ డిఫరెంట్ ఫీల్డ్ అన్నమాట. గ్రావిటీతో ఏమీ సంబంధం లేదు, కానీ మాస్ ఇస్తుంది. అలానే స్టిపులేట్ చేసింది అనమాట. గ్రావిటీతో ఇంటరాక్ట్ అవ్వదు. మాస్ ఉంది కాబట్టి గ్రావిటేషనల్ ఇంటరాక్షన్ ఉంటుంది, బట్ ఇట్స్ నాట్ అ గ్రావిటాన్. It's a standalone particle which gives masses to. It explains the origin of mass. ఇంకా ఏమైనా క్వశ్చన్స్ ఉన్నాయా?
గుడ్ ఈవినింగ్ మ్యామ్.
యా,
విజయలక్ష్మి మ్యామ్. అంటే పార్టికల్స్ అనేవి యాక్సిలరేట్ అయ్యేటప్పుడు కొంత వెలాసిటీతో ట్రావెల్ అవుతుంది మేడం. స్పీడ్ ఆఫ్ లైట్ తో రీచ్ అయిపోయినప్పుడు కొంత రిలేటివిస్టిక్ మాస్ అనేది ఇంక్రీజ్ అయిపోతూ ఉంటుంది కదా మేడం, దాన్ని ఎలా ఎలిమినేట్ చేస్తాం?
ఓకే, సో relativistic almost like close to velocity of light proton interact అయ్యేది. బట్ అప్పుడు ఏమవుతుంది అంటే అదంతా మనకి ఎనర్జీ 1 GeV నెగ్లెక్ట్ చేయొచ్చు. అదంతా దానికి ఉన్న ఎనర్జీ అంతా మాస్ లాగా కన్వర్ట్ అవుతుంది, ఈక్వల్ టైమ్స్ కొలైడ్ అయింది అనమాట. సో వన్ మోర్ థింగ్ ఇస్ లైక్ ప్రోటాన్స్ ఎందుకు యూజ్ చేస్తామంటే ఎలక్ట్రాన్స్ అయితే రేడియేట్ అయిపోతాయి. బ్రెమ్స్ట్రాంగ్ చదివారో లేదో తెలియదు, ఎలక్ట్రాన్స్ సింక్రోట్రాన్ రేడియేషన్ ఇంకా బ్రెమ్స్ట్రాంగ్ చేసి రేడియేట్ అయిపోతాయి, బికాస్ లైక్ దోస్ ఆర్ లైక్ వెరీ లో ఇన్ మాస్. Protons do not have that problem. So protons, even though they acquire this let's say 7 TeV of energy, extra radiation any undadu. So the rest mass energy is 1 GeV, which we can ignore. So this energy gets converted into, of course, like partly into the mass using this E equal to mc square, Einstein's relation.
Thank you, Josh. Anyone else? Online
Yeah.
people, anyone else who want to pose questions?
Yeah, ఇంకా ఏమైనా questions ఉంటే you can always like write to me. So I have shared my email ID.
Sir, principal sir. Okay. Josna, thank you very much. Here, you have explained about all these particles, fundamental particles and all. Really, these people, why? Because I have asked you is, these people have learned something in the fifth paper about particle physics. Our teacher has taught the paper. Sir, Kishore sir has taught the paper and he motivated them related to this particle physics. That's why they have asked, students have asked us to conduct some interactive session. That's why I have asked you to, as I know that you are very much acquainted with this particle physics. And thank you very much for your quick response regarding this lecture. Thank you very much. Thank you, madam.
No, thanks a lot. Like, okay, just before I end, like, నేనంతా చదువుకున్నాను తెలుగు మీడియం. So I'm happy to interact with you, even though online. I would be like happy to interact with you personally. At some time, I'll do that.
Ramesh?
Okay. Thank you very much.
Hello?
Chala.
వినిపిస్తుందా? రమేష్ నా వాయిస్
చాలా.
వినిపిస్తుందా? ఆ పిల్లలకి ఫీడ్బ్యాక్ లింక్ పెట్టాను, సర్టిఫికేట్ లింక్ పెట్టాను, పిల్లలకి చేయించు.
Close చేసామా?
సర్టిఫికేట్
Close
లింక్,
చేసామా?
ఆ సర్టిఫికేట్ లింక్, ఫీడ్బ్యాక్ లింక్.
క్లోజ్ చేసేస్తాము.
ఆ క్లోజ్ కాదు, ఫీడ్బ్యాక్ లింక్.
ఓకే, అందరూ కూడా
నీ గ్రూప్ లో పెట్టాను, నీ వాట్సాప్ పెట్టాను, వాట్సాప్ పెట్టాను.
you can leave now.
ఓకే.
Okay, thanks. Bye, everyone. Thanks a lot, Ramesh, for the opportunity.
నింపితే మీకు సర్టిఫికేట్ వస్తుంది, పార్టిసిపేట్ సర్టిఫికేట్, దాన్ని నింపండి.
ఏంటిది ఎలాగొచ్చింది? చాలా ఇబ్బంది అయిపోతుంది.
చూడండి, ఏదో ఇందులో మోడ్లోకి వెళ్ళిపోయింది, ఎమర్జెన్సీ కాల్లోకి అవుతుంది ఆఫ్ చేసేది వెళ్ళలేదు.
పర్లేదు. క్లియర్ కూడా లైట్ అయితే అలా ఉందని నుంచండి. చూసావా దీని ఎక్స్పీరియన్స్ టెక్నికల్ గిట్ వచ్చి నేను చేసి
టెక్నికల్ అంటే కాదు కానీ రాష్ట్రం అనుకోకుండా టచ్ చేసి